Hi everyone, thanks for coming to this talk. I'm Sungwon Han from KAIST and IBS Data Science Group. Our work is titled Mitigating Embedding and Class Assignment Mismatch in Unsupervised Image Classification. Unsupervised image classification is one of the fundamental tasks in computer vision. Its objective is to determine each data point's membership to one of the predefined class labels without utilizing any label information. Since images are high-dimensional objects, most existing methods focus on reducing dimensionality as they try to discover appropriate decision boundaries. The task of projecting a high-dimensional image to lower-dimensional feature vector is called embedding, and the task of identifying boundaries of dense groupings is called class assignment. Until today, sequential method has been popularly used for unsupervised image classification. This method, illustrated in the left-hand side, operates in two steps. First, it utilizes embedding learning to represent visual similarity as a distance in the embedding space. Second, standard clustering algorithms such as k-means and dbScan are applied sequentially. As shown in the figure, the first step tries to reduce data dimensions without any knowledge of the second step. Therefore, the sequential method may find suboptimal clusters. Joint method tries to overcome this limitation. It simultaneously achieves embedding and class assignment. Examples of joint method are deep cluster, or IIC, which shows remarkable performance gains over sequential methods. Nevertheless, the joint method also bears a drawback that goals for embedding and class assignment are inherently different. Since class assignment loss initially affects how images are embedded, jointly optimizing these tasks again leads to a mismatched result. In fact, mismatches are common. For example, clusters are found by trivial traits such as colors rather than object shapes. While some models propose using Sobel filtered images to avoid trivial clustering, filtered images may lose crucial information. This paper presents a new two-stage approach that overcomes the mismatch problem. Our two-stage process starts with embedding learning as a pre-training step. Then the second stage aims to assign a class for each data point by refining its pre-trained embedding. Adding a pre-training embedding stage can optimize two objectives successfully and avoid mismatched states. Let me go through each of the states in detail. Here is how the first stage works. The ultimate goal is to extract visually essential features without the use of any labels. An ideal embedding should discriminate images of different classes and place them far apart in the embedding space. We adopted ideas from recent research, Super A&D, and Anchor neighbor discovery, which show state-of-the-art performance in unsupervised embedding learning. These algorithms simultaneously discover and gather neighborhoods, guarantee a high entropy in data points, and try to extract invariant features against the data augmentation. We implement three kinds of losses. First, A&D loss for neighborhood discovery. Second, UE loss for high entropy neighborhoods. And AUG loss, finally, for augmentation invariant. These losses are simultaneously optimized from the L2 normalized embedding with the adjustments WT to train our stage 1 model. Now let's look at the second stage. The goal here is to identify appropriate boundaries among classes. An ideal class assignment requires not only ideal embedding, but also grouping with sufficient margins. This goal is realized by two kinds of losses: class assignment loss for setting decision boundaries, and consistency preserving loss for preserving representation power. We define our class assignment loss to maximize the mutual information between the class probability from image and its augmentations. Since mutual information quantifies the mutual dependencies of two random variables, maximizing mutual information between two images can enforce the classifier to learn with invariant features against data augmentation. In the equation shown, the probabilities from the original image and its augmentation are denoted as y and y hat. Note that our embedding from the first stage is auto-normalized, and hence a standard fully connected layer may not be appropriate for training. We introduced the normalized fully connected layer, which does not have any bias term for classification. By regarding each class has its fixed prototype vector, we calculate losses for prediction by just performing dot product between embeddings and prototypes. We additionally add temperature, tau c, to adjust the concentration of feature vectors projected in the unit sphere. Class assignment loss is then defined with a probability calculated from the normalized fully connected layer. Finally, to prevent the model from losing its representation power embedding during the class assignment process, we introduce consistency preserving loss. Let's assume Vi represents an image I and Vi hat as the representation of its augmentation. Since augmented images have the same contents as the original ones, the similarity distance should be closer than in other instances. We calculate Pi hat, the probability of given instance I classified as a jth instance, and Pii hat, the probability of being classified as its own ith augmented instance. By minimizing this consistency preserving loss, the model can revise any misclassified cases over the batches and preserve its representation power. Our second stage model is finally optimized with these class assignment loss and consistency preserving loss. We use the Hungarian method to achieve the best bijection permutation mapping between the clusters and ground truth rate labels. We evaluated the mapping with top 1 classification accuracy over 3 datasets, CIFAR10, CIFAR20, and STL10. This table shows that our proposed model outperforms the baselines substantially. It achieves an accuracy of 81% for CIFAR10, when the existing SOTA is 61.7%. Next, we also tried modifying the first stage unsupervised embedding algorithm to various alternatives. This table describes the embedding quality of various alternatives and corresponding classification accuracy on CIFAR10. Embedding quality is measured for the test data by utilizing the ground truth class labels of the training images, and a weighted KNN or SCBM classifier is implemented upon the encoder. On the other hand, class assignment quality is measured by top 1 classification accuracy for the test data without knowing any training data labels. This table shows the quality of pre-trained embedding contributes to the final classification accuracy significantly. Moreover, when we performed the ablation study on the second stage model, we found that all components in our model contribute to the performance gain, and our full model performs the best. This figure shows the intermediate states of prediction over CIFAR10 during training 2 models, IIC, the current SOTA, and our model. Both models utilize the same mutual information-based loss. Our model shows the organized initialization at first, and performance for every class drastically increases during training. This result implies that our first stage initialization step accelerates the training, while our second stage consistency preserving loss leads to better optimization. When we also investigated the confusion metrics of final models, our model achieved a more accurate performance than IIC. In conclusion, our model can successfully optimize 2 objectives of embedding and class assignment for unsupervised image classification. It outperforms existing baselines substantially and confirms that considerable benefits come from the combination of the embedding learning and the class assignment algorithm. Please come visit our GitHub page for the code and data. Thank you for your attention.